Good afternoon. I am Shelly Singla from GPC Kundi Majra. Today my topic is magnetic lines of force due to a straight current carrying conductor, due to a circular coil and solenoid, and force on a moving charge and a current carrying conductor and a moving coil galvanometer. So first of all we will start with the topic of magnetic lines of force. So, a magnetic line of force is defined as a line of force which can be a straight line or curved line along which a unit test pole, a test pole is a north pole, moves under the effect of a magnetic field. So, this is the definition of a magnetic line of force. So, let us draw a diagram. Suppose we are having a magnet which is having two poles, north and south pole. So, if a north pole is kept near to the north pole, it will be repelled and a line will be drawn which will move from north to south pole outside the magnet. The lines are like this, and these are the lines of force moving from north to south pole outside the magnet and from south to north pole inside the magnet. So, this is a magnetic line of force. Now, we will come to the magnetic field due to a current carrying straight conductor Let us suppose we are having a conductor which is a straight conductor and it is connected by a battery. This is battery. The current is moving from the positive terminal to the negative terminal. So, this is the direction of current. So, we can find the direction of magnetic field due to this current carrying conductor by right hand thumb rule or by right hand screw rule. So, these are two rules with the help of which we can find the direction of magnetic field. If we take the direction of current as the direction of right hand thumb, then curl the fingers. This will give us the direction of magnetic field, which will be the circular lines around this conductor, and the direction will be anti-clockwise. If the current is moving upward, then the direction will be anti-clockwise. But if we reverse the direction of current, like if the current is moving in the downward direction, then the magnetic field will also get reversed. It will be from in the clockwise direction. So, this is the direction of magnetic field lines of force around this current carrying conductor, which is carrying a current I. At any point of this magnetic lines of force, we can find the direction of magnetic field. We can draw a tangent at any point which gives us the direction of magnetic field. So, let us suppose we have to find the magnetic field at this point and we draw a tangent. This gives us the direction of magnetic field at this point. Similarly, at any point we can find the direction of magnetic field with the help of this tangent. So, this direction will be different at all the points of the straight current carrying conductor. One thing we must also remember that this magnetic field will be stronger near to the conductor, that is, it will be more on the conductor. As we go away from the conductor, this will get weakened. So, this is more at the this conductor, and the magnetic field can be increased by increasing the current, the value of current I. That is, more is the value of current I, more will be the value of magnetic field due to this current carrying conductor. Now, next is the magnetic field due to a current carrying circular coil. So, a circular coil is basically a wire which is in the form of a coil. Let us take a coil, and this coil is connected to a battery. Now, we can find the direction of magnetic field at each point of this coil. The current is moving from the positive terminal. So, the direction of current is this. It is moving from positive to negative direction. Suppose at this point we have to find the magnetic field. Again we will apply right hand thumb rule. The thumb will give the direction of current I, and fingers will if we are curling the fingers, they will give us the direction of magnetic field. So, this will be like this, in the form of circular lines around this coil. So, if we take this point, this will be like this. This is the magnetic lines of force. So, at this point, like this. So, if we take this point, so this will be like this. So, at each point the direction of magnetic field will be different. This will be the magnetic field will be circular, near the edges of the coil and straight and parallel in the center. So, next is the magnetic field due to a solenoid. Now, first of all, we will define what is a solenoid. A solenoid is an arrangement of a number of coaxial and circular coils so that each coil has same amount of current flowing in same direction. Let us do basically there are two types of solenoids. First is iron core solenoid and the second is air core solenoid. In case of iron core, there are a set of circular coils wound on an iron rod. So, iron bar is used in case of iron core solenoid, and there is air inside the coils. So, let us draw the diagram. This is an iron rod and this is coils. There are number of coils wound around this iron rod coaxially and circular coils. So, this is the current I flowing in this coil. So, this is the direction of current in each coil. The same amount of current I will be flowing in each coil, and in each it will be in the same direction for each coil. So, this is a solenoid and this behaves like a magnet. A current carrying solenoid behaves like a magnet. So the direction of magnetic field can be given by again right hand thumb rule. If we put the thumb along the direction of current and curl the fingers of the right hand, the magnetic field will be like this. So this will be the magnetic lines of force for a solenoid. Since the magnetic lines are emerging from this end, so this will behave like a north pole and the other end will behave like a south pole. If we reverse the direction of current, then the poles will be also reversed. This will behave like south pole and other will behave like north pole. Now the magnetic field inside the coils is uniform and is represented by parallel, straight, equally spaced, parallel, straight and equally spaced magnetic lines. The parallel, straight and equally spaced magnetic lines show that the magnetic field is uniform inside the solenoid. So it can be increased by increasing the current. If we increase the amount of current flowing in the this coil, then the magnetic field can be increased. And we can also change the material inside the core. We have to remember this this iron core is more permeable as compared to air. So magnetic field will be more for the same amount of current as compared to iron core solenoid. So the magnetic field is more for iron core solenoid than air core solenoid. So this is all about the magnetic field for a solenoid. Now next is the force acting on a moving charge in a magnetic field or Lorentz force. The Lorentz force is also called magnetic force. So let us suppose, let a charge q is moving with velocity v in a magnetic field Let us draw the diagram. So this is a charge q, point charge q, positive charge, and it is moving with a velocity v. So these lines are lines of force or magnetic lines, field lines. So the magnetic field is B, and the charge is moving at an angle theta to the magnetic field B. So the Lorentz force on charge q is Fm vector is equal to q B vector cross B vector. This can be also written as q B vector cross u v v sine of theta into n cap. So the force will be perpendicular to both velocity vector as well as magnetic field. In this case, the direction of force will be inside the plane of blackboard. N cap is a unit vector perpendicular to the direction of magnetic force, and its magnitude is q v v sin theta. So Lorentz force can be also defined as, if we take q is equal to 1 coulomb, velocity is equal to 1 meter per second, and magnetic field is equal to 1 Tesla, theta is equal to 90 degree, then sin theta is equal to 1. In that case, the magnetic force or Lorentz force will be equal to 1 Newton. So a force of 1 Newton is acting on a charge of 1 coulomb moving with a speed of 1 meter per second in a magnetic field of 1 Tesla perpendicular. So this is the definition of magnetic field force or Lorentz force. We can take two cases. If theta is equal to 0 degree, means velocity vector is parallel to magnetic field vector. In that case, sin theta is equal to 0 and magnetic force will be equal to 0. So no force will act on the charge when velocity is parallel to the magnetic field, means charge is moving in along the direction of magnetic field. If theta is equal to 90 degree, means velocity is perpendicular to magnetic field. So sin theta is equal to 1. In that case, magnetic force will be maximum. This will be equal to q v b to n cap. So maximum force will be on the charge q when it is moving perpendicular to the direction of magnetic field. Now the next is force on a current carrying conductor placed in magnetic field Now we are talking about a conductor which is placed inside a magnetic field. Let us draw the diagram. This is a straight conductor of length L and area of cross section is A. So the current is it is connected to a battery. So the current will be along this direction, and the direction of magnetic field is like this. So the angle between the current and magnetic field is theta. Now if the current is from positive to negative direction, the electrons will be moving from negative to positive direction. The electrons are having drift velocity Vd, which is from negative to positive direction. So we have a conductor of length L and area of cross section A, placed in a magnetic field B vector at an angle theta to the current, to the direction of current. So the Lorentz force on one an electron in on each electron is equal to F. This is equal to, as we have discussed earlier, the Lorentz force is equal to the charge itself. The charge on electron is minus E, and the velocity, which is drift velocity Vd, into cross product of drift velocity into magnetic field B. Now the total number of electrons in the conductor is equal to N. This is equal to N AL. Small n is number of electrons per unit volume. This is the density of electrons, number density of electrons, and small n. If we multiply it by total volume A into L, A is area of cross section and L is length, then we have total number of electrons, capital N. Now the total force is equal to capital F. This will be equal to force on each electron into the total number of electrons N. This is equal to minus E Vd into NaL. So this is the total force. Now if we take NeA Vd into L, NeA Vd is equal to current I. If we multiply both sides with L, we have this. Now putting this can be since I is scalar quantity, we can write it as I into L vector. So putting the value of minus NeA Vd L is equal to IL, we have F vector is equal to I L vector cross B vector. So this is the force acting on a current carrying conductor of length L placed in a magnetic field B. F is equal to ILB sin theta. The magnitude of force is equal to IL be sin theta. For theta is equal to 0 degree, sin theta is 0 and the force will be equal to magnetic force